All right, hey guys. Uh, Hope you guys had a good weekend, and ready to do some quantum mechanics this week. Uh, so I think I've gotten everybody's homework, almost everybody's homework. But if you haven't, it's no big deal. Just try to get it to me soon, and I'll try to get it graded soon. But yeah. Anyways, okay. So last time we had started our discussion on perturbation theory. And so we kind of sketched out what the problem is in perturbation theory and how you go about solving it. And in perturbation theory, we're always under this kind of assumption that we can take the Hamiltonian and break it into two pieces, one being a piece that we're familiar with, the form of a Hamiltonian that we're familiar with, and the other a small perturbation on top of that. And so you assume that the simple piece we know the solutions for, and so the solutions for the full Hamiltonian is going to be perturbations on top of that full solution. So we talked about the three cases that we'll be talking about, which are time-independent, non-degenerate perturbation theory, which is what we started talking about last time. We'll also talk about degenerate perturbation theory, time-independent perturbation theory, and then we'll also talk about the case where the Hamiltonian is dependent on time, where the perturbation piece is dependent on time. And that's obviously called time-dependent perturbation theory. So we talked about time-independent perturbation theory. We said that the basic idea is that the solutions, in other words, in our language, the kets we can write them out as perturbative series, where the first term is going to be the solution to the simple piece of the Hamiltonian, and the eigenenergies can also be written as a perturbative series, right? And the superscripts are put on here just as a kind of a bookkeeping convention, so you can keep track of the number of times the perturbation comes into play. Right. So what do we do? So we started out with the general problem. So we're assuming that there are some solutions, some eigen kets of this full Hamiltonian, and the eigenvalue takes the normal form, right? So what we did last time was we plugged in our form of the Hamiltonian, which is the simple plus the small piece, and then we plugged in our perturbative expansions and multiplied everything out and matched powers of the perturbation, right? And at zeroth order, we got back out our simple Hamiltonian or simple eigenvalue equation. And at first order, we had to use multiplication from the left by an eigenbra, so we could evaluate the simple part of the Hamiltonian. And we saw some things cancel out, and we ended up finding that the first order energy correction is just the expectation value of the small piece of the Hamiltonian with respect to the unperturbed kets. Right? And then we went on and talked about the solutions, or the first order eigen kets, and for those we had to work out this one particular coefficient, which is the overlap between the first order correction with some other eigenbra where m here is not equal to n. And there we use the fact that these guys are normalized, right? And went on and showed that after some different little tricks here and there, we ended up finding that, I'm trying to get to the, here we go. We ended up finding that the first order energy correction goes like, goes as an expansion in the unperturbed kets, but these are kets that are orthogonal to the zeroth order piece of the n eigenket. Okay, and so they come in at first order of the perturbation, so that's a good check on what we're doing. Okay, so what I want to do today is continue this discussion, and then we'll talk about a simple problem that we can solve exactly, but we can use to check our formalism for time-independent perturbation theory. So let's do that. So let's take a look at this the solution we had last time. Okay, and like I was just saying, you can see that this solution is orthogonal to the unperturbed ket, right? The N0. And for perturbation theory to work, it turns out that this is actually a requirement of the perturbed kets, and you can work through it and see how this comes about. Okay, so let's do that, and hopefully it'll give us some insight into how these eigenkets are constructed. Okay, so again, let's go back to our first order equation. So let me flip back here and get back to our first order equation. Remind us where it came from. It's this guy, right? So here's our first order equation that we got from expanding out the full eigenvalue problem and matching to the first order terms. So what I want to do is move these things around so that I get the unperturbed Hamiltonian being subtracted by the unperturbed eigenvalue hitting on this perturbed ket. While on the other side, I've got the perturbed energy, the perturbed Hamiltonian acting on the unperturbed ket, right? And from this, we can see that the left-hand side of the equation is going to be invariant under a particular type of transformation, right? So it's a transformation where we take this N1 and we shift it by some piece that's proportional to the N0. And here A can be any arbitrary constant, okay? And the way we can see that is by taking this and plugging it in and make sure that we get back what we started with, right? And you can see that when I plug this in, what's going to happen is I'm going to get, again, this stuff hitting the perturbed ket, which we don't know what the result of that is, but we do know the result of H0 hitting this N0 term, and that's going to give us this difference like this, right? So H0 when it hits this is going to give me En0, and so that term is going to drop out. And so even after this transformation, I get back to the same thing I had on the left-hand side from the beginning. All right, so this is telling us something about our eigenkets, right? And to see what it is, let's continue on here. Okay, so let's say we were able to solve for N1 and E1, so our first order perturbed eigenket and eigenvalue, right? Then what this is telling us, what this invariance under this transformation is telling us, is that this thing is also a solution, right? But in quantum mechanics, we're interested in finding unique solutions, right? And so what we have to do is require that these the first order kets are actually orthogonal to N0, and that's what we noticed back here when we got to the solution. We could see like explicitly that it's going to be that's going to be orthogonal. And this little argument that we went through kind of shows that explicitly why you have to do that. So what we have to do is we have to require not only the first order, right, but to all orders above above the zeroth order, they all have to be orthogonal to the unperturbed eigenket. Okay. All right. So finally, before we move on to the example, let's work out the second order correction to the energy eigenvalue. Okay, and most books you'll see that they'll do this. Not only will they do this, but they'll work out the second order corrections to the energy eigenket, but you never actually need it. All right, I mean you hardly ever, and I'll never give you a problem where you have to solve for the second order energy eigenket because it just gets messy. So if you look in a book, you'll see what I'm talking about. Okay, and so that reminds me to remind you guys that that if you haven't taken the qualifier, or if you have and you still need to pass the quantum part, which hopefully you're not in that situation, but just know that, the stuff I'm covering here for our, in perturbation theory, is fair game on the qualifier. Okay, so make sure you understand, things to first order, right? The things that we've been talking about. So you won't have any tough, like, time dependent perturbation theory problems, but you will on occasion see time independent, both degenerate and non-degenerate perturbation theory problems. Okay, so that's my spiel about that. All right, so let's get back to second order energy correction. Okay, so what we want to do is we want to go back to our equation, our exact equation that we expanded out. Go back here to equation 6, which is, again, our everything where we plugged in all the expansions. And we'll expand everything out and match to second order this time. And when we do that, we have 5 terms here. So we have 2 on the left and 3 coming from the right. Right? And like we did last time, we want to be able to evaluate or try to get rid of this Hamiltonian here, so we can hit it from the left with the 0th order eigenket. Right? So that'll allow us to get a number out of this guy. Right? And then we can use the fact that N0 and N2 are orthogonal. Right? We just showed that they have to be in order to find unique solutions to the general problem. So that term's going to go away. That's going to go to 0. And likewise, on the right-hand side, we'll have N0 hitting 0. Both of those terms now we know will go away automatically. And the N0 term, when it hits this guy, is just going to give me 1, right, times the second order energy correction. So what we have are only really 2 surviving terms. So we have the second order energy correction is equal to this matrix element over here, right? We're here N1, again, we know what the expansion of it looks like, right? But let's, before we try to use that, let's plug in or multiply by 1 in between this first order, or the perturbation Hamiltonian, and this first order energy eigenket. And we'll do that in terms of a completeness relation. Okay, so the reason I'm doing that is because now when I do this, and I know that because these guys have to be orthogonal, this sum over m naught cannot include n naught, right? Or it can, but it's just, that term's going to give me 0, right? So I can actually simplify this sum a little bit by just dropping that term, right? And so what I have now is the relationship that we derived earlier. Let me just remind you by going back here when we were working through the first order energy eigenket. So we have this same coefficient here with this guy. And if you look, you see that we've got this thing that we originally had times this guy, and these guys are just the Hermitian conjugate of each other, right? Because we know that H1 has to be Hermitian for the Hamiltonian to correspond to an observable. Okay, so what that means is, in the end, we can write the second order energy eigenvalue that as the sum over m naught, where m naught can't be n naught, of this stuff right here. So we've got the matrix element squared between n naught and m naught divided by this energy term, right? And if you count up, or if you just count the number of what am I trying to say? The number of times the perturbation shows up, you see it showing up twice, and that's what we would expect for a second order energy eigenvalue, okay, or a second order correction, okay. So don't get confused by thinking, oh, it's second order, so it's going to be order energy squared. No, it can't be, because it's energy, but it's going to be second order in the parameter that we're expanding in, okay. Okay, so that's the formalism for time-independent, non-degenerate perturbation theory. Okay, what I want to do next is work through a simple problem that I'm sure I've assigned on homework, and you guys have seen it on homework. Maybe we even talked about it in class. I can't remember, but it's a good problem because you can solve it exactly, right? And then do an expansion, and then you can test your perturbation theory by doing the expansion from the get-go, all right, using perturbation theory. Okay, so let's see how this works. So this is the so-called two-state problem. Okay, so you got two states that we call 1 and 2, right? And we have that we've written the Hamiltonian here in terms of the unperturbed kets. Okay, so we have two diagonal terms. So this guy's going to give me a diagonal term, and this guy's going to give me a diagonal term. And then we've got two off-diagonal terms, right? And they can each have their own different coefficient. So here I'm calling this guy V12 and this guy V21. And I've introduced a small constant here, lambda, that we're going to use to expand in. Okay, so it's going to be our perturbative constant, our expansion coefficient. Okay, and the assumption here is that this guy is small. Okay, so we know the Hamiltonian has to be Hermitian, right? And let's just assume for the case of just for simplicity that V12 and V21 are real. And so because the Hamiltonian is Hermitian, that means that V12 equals V12 star and V21 equals V21 star, and V12 has to be equal to V21. Okay, so that simplifies our lives a lot because now I can just write this guy as just one constant, right, and pull it out in front. Okay, and so that's what I've done here. So this is a typical form of the two-state problem when you're given it to solve. Okay. And so the way we would solve this is we would form the Hamiltonian matrix, right? So the way I would do that is form a matrix between the 1 and 2 kets, right, with the 1 and 2 bras, right? And so this guy's going to give me this diagonal term. This guy will correspond to this diagonal term. And then I'll get two off-diagonal terms from this guy, okay? Easy stuff, okay? So now we've got the Hamiltonian matrix, and anytime we're working in matrix mechanics and we want to find the eigenvalues, we need to just diagonalize the Hamiltonian or solve the characteristic equation, right? So that's what I'm doing here, okay? So I'm taking the determinant of this guy after I've subtracted off the eigenvalue part. And going through some algebra here, we get something that looks like this. So we have to use a quadratic formula. So I get two energy eigenvalues that look like this, okay? And I can pretty it up a little bit, and I end up with a solution that looks like this. So I get basically the average of E1 and E2 plus or minus this stuff under the square root, okay? And so if we were just, this is the exact solution, right? So if we were, not worried about perturbation theory or anything like that, we could just stop at this point. But now let's say, oh, well, lambda is very small. Okay, so if lambda is very small, then maybe I can get a simpler looking solution by doing a Taylor expansion. Okay, so let's do that. So let's assume lambda is small. So it's some number between 0 and 1. And we want to try to obtain an approximate expression that's simpler looking and captures most of the captures the physics, right? Really. Okay, so let's do that. So let's take this guy and Taylor expand it. Okay, so I'm going to pull out this factor here so I can get something like 1 plus some stuff. Right, and I'm going to expand to the square root. So I get 1 plus 1/2 times this stuff plus higher order terms. Okay, and let's just we're going to work to lowest order in lambda here. All right, so if I multiply this stuff out, I end up with something like this. All right, so you see the plus signs and the minus signs. And so in other words, I get two approximate energy eigenvalues. So I get one that goes like the unperturbed energy eigenvalue plus this correction term. And then I get the energy eigenvalue E2, which is proportional to the unperturbed E2 minus this correction term. Okay, and yeah. So I'll come back to the physics of this in just a second. Let's work through the perturbation part. Okay. So these are our exact solutions that we expanded. Okay. But now what I want to do is try to solve this problem using perturbation theory. Okay. So what we want to do is we want to go back before any of this diagonalization stuff and look at our Hamiltonian, okay? And what we're going to do is we're going to split this into two pieces. Okay, so I'm going to split this guy into first these two terms, which I'm going to call the simple piece. And the reason I'm calling it the simple piece is because it's diagonal, right? So you already know what the energy eigenvalues are. And the small piece is going to be this off-diagonal stuff, okay? All right, so let's get back down here. Okay, all right, so I have my simple Hamiltonian, and I've got my first order correction to the Hamiltonian. All right, and now at this point, we've already worked through all the formalism, so all we need to do is go back and look at our formulas, right? So if I want the first order energy correction, I go back here and I say, okay, first order energy correction is the perturbed Hamiltonian sandwiched between two unperturbed eigenkets. Okay, and if I look at what I have, the perturbation Hamiltonian looks like this. It's a 1-2 plus a 2-1, right? And so what happens is if you put that between two unperturbed kets, right, that's going to give you 0 because these guys are orthogonal, right? So this term would give me, this 1 on 1 is going to give me 1, but this 1 on 2 is going to give me a 0. And likewise for this term. All right, so at first order, we just get back the unperturbed energy eigenvalue, and it works the same way for E2. Okay, so E2, you'd get the same thing. So apparently what we need to do is go to second order in the perturbation to get any, to compute any corrections to our unperturbed energies. Okay, and that actually, now that we've solved the problem exactly and expanded, we can go back and we can look and say, oh yeah, of course, we can see here that that this perturbation is coming in at second order. So if we're solving this problem approximately using perturbation theory, it makes sense that first order energy corrections vanish and we have to go to second order. Okay, so what I'm going to do is just apply our formula that we derived. Where was it? Was it here or was it at the beginning? Yeah, it's at the big. That's up here. Sorry. Our second order energy correction is right here. Okay, so you see that we have a sum over m naught here, right? Where m naught can't be n naught. All right. So you see the subscript n here and n here, right? So for E1, the second order energy correction will be 1, 0, H1, and then we sum over this M value here. Okay, so let's go back down here, right? And let me do that. So here's E1, all right? So we get the E1 0 term plus, and like I said, we're summing over this coefficient here, I, okay? And we have two possible values that I can take. All right, so I expand those out, and what I find is that the only piece that's going to, give me non-zero contribution is the I equals 2 piece, right? Because we're already seeing that the I equals 1 piece vanishes. So I can plug that in, right? This guy's going to give me 0, but this term is going to give me a 1, and then I'm going to get this thing squared, okay, all over the energy difference between E1 and E2, okay? And likewise, we can do the same thing for E2, right? So I can have E2, the unperturbed energy eigenvalue here, and plug in my formula for E2, right? So now I'm going to be summing over this guy, right? And now I have 2 here, right? And so if I sum that over, I can see that, again, only one of these terms is going to give me a contribution, right? And that leaves me with lambda V12 squared. And so I square that out. And now I have E2 minus E1, right? So where before for E1 I had E1 minus E2. So let's put them in the same order so I can pull out a minus sign, right? And I see that E2 is equal to the unperturbed E2 minus lambda squared V12 squared over the difference of the unperturbed energy eigen values. And you can see if you go back and look that that's exactly what we got in solving the problem exactly, and then applying that approximation and expanding. Okay, so this was a simple case where we could solve it both exactly and apply our perturbation theory, and we can see that at least to lowest order we're getting the same terms, right? We're getting the same values. And this isn't always the case, but the perturbation theory is just meant to give you a very a good approximation to the exact solution. Okay. Right, so we see that perturbation theory matches, right, in the case of a small lambda, okay? And one of the things that you notice is that let me go back here where I can get them both on the same screen. Right, so let's look at the energy eigenvalues here, and you can see that what happens, right, is that E1 gets pushed up, right? This is all, let's assume E1 is greater than E2, right? So here, this thing would get pushed up, whereas this guy would get pushed down, right? And even as I increase, the strength of lambda, let's assume that we could, turn a knob and change the parameter, right? And so what we see is that these energy eigenvalues get further apart, right? And this is a general result of perturbation theory, or anytime you have these types of problems where you introduce some non-diagonal terms, right? Is that you see that the perturbations never cause the energies to cross. In other words, I would never have the case where E1 would get smaller and E2 would get bigger, and then at some point E2 would be greater than E1. You would never see that, right? And it's actually a famous theorem. It's called the no crossing theorem, right? And it turns out to apply to all cases in perturbation theory. Okay. All right. So that's it for this lecture, and next time we'll pick back up and work through, I think, some more examples, and then we'll start to get into maybe some degenerate perturbation theory. Honestly, I have no idea. I haven't looked at the notes for next time, but I think we're going to work through some examples. Okay. And in the meantime, I'll try to find some homework problems to give you, but I'll let you know when I put those in the Dropbox. Okay. All right. Well, have a good week, and I'll talk to you on Wednesday. All right. Bye.